In this section, we're going to be looking at some more things about functions and their graphs. And in this section, we're going to be identifying intervals on which a function increases or decreases or is constant. We're going to be using graphs to locate the relative maxima or minima. Also, we'll be identifying even or odd functions and recognizing their symmetries, and also understanding and using piecewise functions. All right, we're going to look at some of these definitions of what increasing and decreasing functions are. And in this case, it says a function is increasing on an open interval, which is called I, if for any x1 and x2 in the interval where x1 is less than x2, then f of x1 is less than f of x2. So here we have an increasing function here on the left-hand side. And it's increasing between two values here, x1 and x2. Here, the value of f of x1 is less than the value of f of x2. So we can say that this function is increasing on an open interval. And then the other one is this. A function is decreasing on an open interval if just I, if for any x1 and x2 in the interval where x1 is less than x2, then f of x1 is greater than f of x2. This is pretty much a function that's decreasing because here's x1, and this is where f of x1 is. And there's x2, and there's where f of x2 is. You can see the value of f of x2 is less than f of x1. So that means it's decreasing. And also, a function is constant on an open interval, I, if for any x1 and x2 in the interval where x1 is less than x2, f of x1 equals f of x2. Here, you got x1 here, and then there's f of x1, and then x2, and then f of x2. That's a constant function. That means it's constant because both the value of f of x1 is the same as the value of f of x2. Okay, so the open intervals describe where the functions increase, decrease, or are constant. And we use only the x coordinates and not the y coordinates. Okay, and we're going to look at an example of just that. Like this particular problem here that I've already done. State the intervals in which the given function is increasing, decreasing, or constant. And here's the graph of that function f of x. In this case, f of x is equal to x to the third minus 3x. We can see that this graph is increasing from negative infinity up to negative 1. Okay? Because that negative 1 is up to some maximum value. Now keep in mind we're only dealing with x values, not the y coordinates, just the f of x, just the x values. Okay? So it's increasing from negative infinity, and at 1 it hits a maximum point. So it's increasing on the open interval from negative infinity to negative 1. And then it starts decreasing between negative 1 and positive 1. Okay, so here it's decreasing from negative 1 to positive 1. And then after negative 1, it starts increasing again from 1 to infinity. So these are the intervals that the function is increasing. It's increasing from from negative infinity to negative 1, and from 1 to infinity. And then it's decreasing between negative 1 and positive 1. Okay, and it's always open intervals. Okay, and we're only dealing with the x coordinates in this case, not the y coordinates. All right, the next term is relative maxima and minima. In this case, a function value f of a is a relative maximum of f if there exists an open interval about a such that f of a is greater than f of x for all the x in the open interval. Okay, so here this one has a relative maximum right here. That's the highest point that the graph reaches before it starts declining. And then the function value, f of b, is the relative minimum of f if there exists an open interval about b such that f of b is less than f of x for all the x in the open interval. That's the lowest point. So right here, this is the relative minimum, the lowest point here on this graph before it starts increasing. Okay, so know the difference between relative maximum and relative minimum. And if you look at this example, we want to find out what are the relative minimums and the relative maximums. Okay, now in this case, the relative minimums are those lowest points on this graph. In this case, the lowest point here looks like it's negative 1, 2, 3, 4, 5, then down 1, 2, 3, 4, 5. So negative 5. Negative 5 is a relative minimum. Another relative minimum is 0, 0. And then here's another low point right here from 5 to negative 5. Those three are relative minimums because those are the low points on this particular graph before they start increasing. All right, now for the relative maximum, it's these 2 points up here. This one is negative 2 and 2. And the other one is the ordered pair 2, 2. Okay, so the relative minimum and relative maximum are ordered pairs. Okay. So know how to identify relative minimum and relative maximum in a graph that's given to you. All right, the next thing we'll look at is even and odd functions and symmetry. And we'll look at the definition of even and odd functions here. An even function is when you replace your x with negative x, you should get the original function back, which is f of x, which means the right side of the equation does not change. And then an odd function is when you replace your x with negative x, you're going to get the opposite of f of x. That means that every term on the right side of the equation changes to the opposite sign. Okay? Every term has to change to the opposite sign for you to have a odd function. And we're going to look at some examples of just that. And here are 3 of them. Let's say we want to determine whether each of the following functions is even, odd, or neither. In this first problem, we got f of x is equal to x squared plus 6. Okay? This is f of x is equal to x squared plus 6. And we want to determine whether this function is even or odd or neither. And we do that by replacing each x with negative x in this particular function. So when x is replaced with negative x, you're going to have negative x, and that's squared plus 6. Now negative x and u squared will be negative x times negative x, which will be a positive x squared. And then plus 6. Now compare that with the function f of x. Notice I did get the original equation back when I replaced the x with negative x. So I can conclude that this particular function is an even function, because I came up with the original equation when I replaced the x with negative x. Okay, now part B is g of x, and that's equal to 7x cubed minus x. G of x is equal to 7x cubed minus x, and I want to determine whether that function is even or odd or neither. Again, we replace the x with negative x. So that means we're going to have 7 times negative x as cubed minus negative x. Okay, now negative x cubed is negative x times negative x times negative x, or it'll be negative 7 x to the third. And then minus the negative x will be plus x. Now compare that with your g of x. Each term changed to the opposite sign when the x was replaced with negative x. So we started off with 7x cubed. When we replaced the x with negative x, we ended up with negative 7x cubed. We started off with minus x. When we replaced the x with negative x, we came up with plus x. So that means that this function can be considered as an odd function. And then finally, part C. This is h of x is equal to x to the fifth plus 1. H of x is equal to x to the fifth plus 1. Now, we want to determine whether that function is even or odd or neither. And again, we replace the x with negative x. So that means this will be negative x, and that's raised to the fifth plus 1. Now, negative to an odd power is going to be negative. So this will be negative x, and that'll be to the fifth power plus 1. Compare the h of x with h of negative x. Only the first term changed to the opposite sign. The second term did not. Okay, x to the fifth changed to negative x to the fifth, but the plus 1 remained the same. So it's neither odd nor even. So we can just say neither. Okay, so be mindful of how to determine whether a function is odd or even by just simply replacing the x with negative x in these type of functions that are given to you. All right, the next thing we'll look at is symmetry and how even and odd functions are related to symmetry. Okay, an even function along with y-axis symmetry is this. If you replace your x with negative x and you get f of x, that's going to be symmetric with respect to the y-axis. A good example of that would be this particular function, y is equal to x squared. And usually the graph of the function y is equal, well, f of x equals x squared looks like this. That's what the graph looks like. Notice that the right side of this graph has what we call the mirror image of the left side of the graph. That's what we mean by y-axis symmetry. Here's the y-axis here. And the right side has the mirror image of the left side of this graph. And then odd functions and their origin symmetry is this. If you replace your x with negative x and you get the opposite of f of x, that's going to be symmetric with respect to the origin. Let's say we have this function f of x is equal to x cubed. That's a particular function that's going to be odd, and the graph will look like this. And usually that's an odd function because if I take this top part of the graph and rotate it, that top part will fit on this bottom part of the graph right here. So this part has the mirror image of this part right here. That's symmetric with respect to the origin. Okay, so those are just a couple of examples of how an odd function has a relationship with the origin symmetry. And this one, the even functions, this one has a relationship with y-axis symmetry. Okay. All right, the next thing we'll look at is piecewise functions. Now, a piecewise function is defined by two or more equations over a specified domain. It's two or more equations over a specified domain. And one good example of a piecewise function would be cellular phone plans. Those can be represented by using a piecewise function. Okay. And here's an example of a cellular phone plan that has a piece that's written in the form of a piecewise function. Here we're going to use the function that describes the cellular phone plan. C of t, which is going to be the cost, that's going to be equal to 20 if the time, which is t, is between 0 and 60. And that does include 0 and 60. Or 20 plus 0.40 times the quantity t minus 60 if t is greater than 60. And here we're going to use that particular function to find and interpret each of the following. So here we want to find the cost of this cell phone plan at $40. So here's part A. The cost at $40. Now using this piecewise function, 40 is between 0 and 60. So that means that this cost is only going to be 20. So the cost for 40 minutes of time used on this cell phone plan will just simply be $20. Okay. Now part B is the cost for 80 minutes. C of 80. Now notice that the 80 is bigger than 60. So we're going to use this one, the one at the bottom, which is of course 20 plus 0.40 times, now t is 80, so that's going to be 80 minus 60. And that's the formula I'm using. I'm just replacing the t with 80. Okay, now let's simplify this. 80 minus 60 is 20, so this will be 20 plus 0.40, and 80 minus 60, that's 20. And then we'll do 20 times 0.40, which will be 8. So this will be 20 plus 8, or $28. So the cost for 80 minutes of time used on this cell phone plan would just simply be $28. Okay, that's how we use a piecewise function to evaluate certain expressions. Okay, so that's just one application there. Now, let's look at another piecewise function. We want to evaluate the piecewise function at the given values of the independent variable. Now here we got a piecewise function f of x is equal to, we use 5x minus 1 is if x is less than 3, or 7x plus 2 if x is greater than or equal to negative 3. Because these values of x will tell you which one you're going to have to use. Okay. One common mistake that I see is that people will evaluate both of these functions at that value, but you have to look at the conditions here. You only use the 5x minus 1 if the value of x is less than 3. And you only use the 7x plus 2 if x is greater than or equal to 3. Okay? So now let's look at part A. We're going to evaluate f of 1. And x is equal to 1, so we need to use this one because x is 1 and it's less than 3. So we have to use that 5x minus 1. Okay, so we're going to replace this x with 1. So we have 5 times 1 minus 1. And then we simplify that. 5 times 1 is 5. 5 minus 1 is 4. So the value of this piecewise function when x is equal to 1 is going to be 4. Okay, now the b part. F of 7. Now here, x is 7, and 7 is greater than or equal, 7 is greater than 3, so we got to use the 7x plus 2. Okay? Here 7 is bigger than 3, so we have to use the second one, 7x plus 2. So we're going to replace the x with 7, so you're going to have 7 times 7 plus 2, and then 7 times 7 is 49, plus 2, that'll be 51. So the value of that piecewise function when x is 7 will be 51. And then the c part, you have f of 3. In this case, 3 is equal to 3. So we got to use 7x plus 2 because we have the condition where x is greater than or equal to 3. That means 3, 4, 5, 6, 7 on up. And 3 does equal to 3, so we do use the 7x plus 2 to evaluate this. So it'll be 7 times 3 plus 2. And then 7 times 3 is 21. 21 plus 2 is 23. So the value of that piecewise function when x is equal to 3 is simply 23. Okay, so do be familiar with how to evaluate piecewise functions at their specified values. Okay, and that will do it for this particular section on more of the things that deal with functions and graphs.